Hey everyone, it's Alice here from Top Mark Science, and today we're going to be looking at turning forces. Throughout this video, we will be exploring the meaning of the term moment, examples of using moments and levers in everyday life, and calculating moments. Let's get started. Without realising, you have probably used moments and levers to help you complete everyday tasks. They make things easier for us. Take this door for example. How does it open? Well, on one side we have hinges that help the door swing open and close around a point, and a handle on the other side. But where do we put this handle and why? Imagine putting the handle right here, right next to the hinges. Would the door open so easily? No. If it's too close to the hinges, it would require a larger pull force from you. We can make it easier for ourselves by placing the door handle further away, and so less force is needed to open the door and it becomes easier. This concept is all to do with moments. Moments are described as the turning effect of a force. In the case of our door, we applied a force. We pulled the door handle, and the door opened because it can rotate around a fixed point. This is called the pivot, which is defined as the point around which an object can rotate. We'll come across more of these in a bit. Pause the video here and have a go at the tasks on the screen. Identify the terms moment and pivot, then identify where the pivots would be in the items in the pictures. If you finish, try the challenge. Let's see how we got on then. Marking pens ready and annotate your work as we go. Firstly, a moment is the turning effect of a force. A pivot is the point an object rotates around. Well done if you got these definitions correct or near the same. On the screen are now the pivots for the objects in the diagrams shown by the green stars. You might notice that most of them are in the middle of the object themselves, but this will not always be the case, such as the spanner. It just depends by which point the object is moving around. If you had a go at the challenge to sketch a diagram of each to show the force applied and moment made, well done. If not, feel free to make notes as we go. So starting with the spanner, the force will be applied at the top, opposite the screw or nut we are trying to turn. At the pivot, we can turn it clockwise or anti-clockwise depending on whether we want to tighten it or loosen it. By applying this force means the spanner and nut have a turning effect, which is the moment. The opposite direction would look like this. Lefty-loosey, righty-tighty. Now the scissors. We can cut paper by squeezing the finger holes together. This would be our force, and this causes each blade to move about the pivot, resulting in the blades turning and moving together at the end. This turn is the moment. If you wanted to open up the scissors, the arrows would point in the opposite direction. A seesaw is a popular example, where you might have unbalanced forces causing one side to drop. So the seesaw moves about the pivot point, creating a turning and lifting effect, the moment. And it would be the opposite for the other side, but work in exactly the same way. But even the other side is turning as a result of an imbalance, so there is still a moment on this side too. This is called the clockwise moment. More on this a little bit later. And finally, opening a can of paint with a screwdriver. It's very hard to do this with just your hands, hence the use of a screwdriver, which acts as a lever. Applying a force down on the screwdriver moves it about a pivot at the point of contact between the screwdriver and lid, causing a moment and lifting the lid in the process. Now, how big or small a moment is dependent on two things: the size of the force applied to the object and how far away the force is applied from the pivot. This distance should be perpendicular to the pivot. For example, I can use 20 newtons of force on the end of a spanner, acting 0.2 meters away from the pivot. If I multiply these together, it gives me a moment size of 4 Newton meters. Pause the video here and have a go at the practice questions on the screen. The equation is at the top for you to copy and use to help you. If you finish, try the challenge. Let's go through the answers. Be ready to annotate your answers as we go. Question 1. Calculate the moment when a force of 10 newtons is applied at 0.3 meters from a pivot. Well, we've already been told that moment is equal to force times perpendicular distance from the pivot. The question tells me there is a force of 10 newtons applied at 0.3 meters from the pivot. 10 times 0.3 gives me 3 Newton meters. It's important to remember your units. Question 2. Calculate the moment when a force of 5 newtons is applied at 50 centimeters from a pivot. Again, using the same method, I have 5 newtons of force applied 50 centimeters from the pivot. However, I should convert these into standard units for distance, which is meters. So 5 multiplied by 0.5 gives me a moment of 2.5 Newton meters. Question 3. A person pushes on the middle of a door with a force of 20 newtons. The distance between their push and the hinges is 0.5 meters. What is the moment used to open the door? Same again, 20 newtons times 0.5 gives me 10 Newton meters of moment. Question 4 requires some words instead of numbers. We're going to use our knowledge to explain how pushing the edge of the door makes it easier to open. But we can still use the equation to help us because, remember, moments are connected by force and distance. Therefore, pushing the edge of the door makes it easier to open because it increases the distance of the force from the pivot, the hinges, which increases the moment to open the door. Last question. A person rotates a spanner with a moment of 12 Newton meters. The force is applied 25 centimeters from the pivot. Calculate the force. Now here, we'll need to use some math skills to complete an additional step. You may have seen triangles like this. So far, we've been calculating moments, which is force times by distance. Highlight or cover the thing you want to find out, which reveals the remaining equation to help you rearrange it. In this question, we've been asked to calculate the force, so by highlighting this, leaves me with moment divided by distance. Always work from the top of your triangle to the bottom, and the middle line is a divided by, so we're left with moment divided by distance. Substituting my numbers in gives me 12 divided by 0.25, leaving me with a force of 0.125 newtons. Trickier, that one. Rearranging equations is worth practicing. They don't only crop up in maths. Let's go through the challenge. On a seesaw, you have 500 newtons on one side and 300 newtons on the other. How can we make the seesaw horizontal? We can show this visually with boxes, 500 newtons on one side and 300 newtons on the other. Typically, when placed at the edge, would result in an imbalance of forces, and so the seesaw drops on the side with a greater force, which is 500 newtons, so we can do something to change this. All we need to do, and you can trial this next time you find yourself on a seesaw, is move the larger force from the edge to reduce the distance to the pivot, so that the clockwise moment equals and balances the anti-clockwise moment. Let's go through an example together. A seesaw needs to be balanced. One side, 2 meters from the pivot, is a box which has a weight of 20 newtons. And on the other side is a box which has a weight of 30 newtons. Calculate the distance needed between the mass which has a weight of 30 newton box from the pivot. So to make this more simple, I'm going to divide my seesaw into 2 parts and then start to label the diagram with what I already know and have been given to me from the question. I will read the question again and fill it in as I go. A seesaw needs to balance. On one side, 2 meters from the pivot is a box which has a weight of 20 newtons. So far, I have force and distance. Therefore, I can calculate the clockwise moment. Because moment is force times by distance, as we practiced earlier, so I can calculate 20 newtons times 2 meters, which gives me a clockwise moment of 40 newton meters. Therefore, in order to balance, as we briefly mentioned earlier, the clockwise needs to be the same as the anti-clockwise moment, so I can label this side with a moment of 40 newton meters. So on my side of interest that I'm trying to find out, I have a force of 30 newtons and a moment of 40 newton meters. Inputting these into my rearranging triangle, I can now work out the distance it needs to be to balance. If I work from the top of the triangle to the bottom, it will give me the moment divided by the force, which is 40 divided by 30, resulting in a distance of 1.33 meters that the box needs to be from the pivot in order for the two weights to balance. Phew! Let's try again, so feel free to join for the challenge. A seesaw needs to balance. On one side, 3 meters from the pivot, is an item which has a weight of 6 newtons, and on the other is a box which has a weight of 4 newtons. Calculate the distance needed between the mass, which has a weight of 4 newtons, and the pivot. Now on one side I have force and distance, so I can calculate the moment by multiplying these two together. 6 times 3 gives me an 18 newton meters anti-clockwise moment. And to balance this needs to be the same for the clockwise moment, so this can be 18 newton meters too. On the right hand side, I now have the force on the seesaw and the moment. So I can calculate the distance working from the top of the triangle to the bottom, and that will give me a moment of 18 divided by a force of 4, which is a distance of 4.5 meters to balance out the heavier weight on the opposite side. Well done if you got any stages of that. That's a tricky one. Putting maths to one side then, as we saw earlier, we can use moments to our advantage. We can make smaller forces larger through the use of levers. Take 2 spanners for example, one small and one large. They have different distances from the pivot point to the force. The one with the longer distance, e.g. a long spanner, reduces the force to turn, making it easier to screw or unscrew. Levers, such as using a screwdriver to undo a paint can, a longer screwdriver increases the distance, therefore less force is required to open the can, so it's easier to open with the longer screwdriver. You guys have done really well today. Let's see what we have learned. Question 1. What word goes with this definition? The turning effect of a force. A moment. Well done. Question 2. Arrange these words to make them into moment equations, so using force, moment, and distance. Moment equals force times by distance from the pivot. Question 3. What units are moments measured in? Newton meters, or nm for short, but it must be a capital N with a lowercase m. Question 4. How can two objects of different weights balance on a seesaw? Move the distance from the pivot so the clockwise moment balances the anti-clockwise moment. And final question, number 5. What does a longer spanner, or why does a longer spanner work better to undo a tight bolt? It increases the distance from the pivot, which reduces the force needed to turn. Take a couple of minutes to rag your progress from this video. It will help you understand what you might need to look back on in the future. Thank you so much for watching this video, guys. If you enjoyed it and would like to see more from Top Marks Science, you can like this video and subscribe to my channel. Thanks for coming, and I'll see you next time.